Right, this is question 5. We are slowly getting to the end, so don't worry about that. Yeah, just making sure it's still recorded. So, this is a graph for question 5A. So I'm just going to draw the graph out. I'm not going to draw it specifically, I'm just going to draw the general shape. Trying to draw it a bit more accurately than that. So it goes something like this. They meet at the same point. They do meet at the same point. That's A and that's B. State which feature, for 5A it says state which feature of this graph confirms that the rubber cord is elastic. Well, one thing you could say is that that it's been stretched and there's no permanent extension, as though points meet at the same point, so there's no plastic deformation. So it shows that it's not plastic and it regains its original shape after the weight has been taken off it. As A is the loading, B is the unloading. As they've arrived at the same point, the overall effect of the weight on the extension, the permanent extension, there is none. So as you can see, I'll zoom it in on the camera. A is the extension, and as you can see there is no extension overall. So we can say that this shows the material is plastic, elastic even. And carrying our day as normal. See if that's what it says in the mark scheme. Yep, so no permanent extension. It says 5B. So I'll just, after 5A, I'll just put a little point saying no permanent extension. Extension. 5B. It says, explaining your method, use the graph curve A to make the work done in it, producing an extension of 0.3 meters. So, there's 0.3 meters. It's approximately about here on the graph. 3 meters. So what you need to do for this, obviously I can't do it exactly because mine's not labelled out, but what I'm going to shade in here, I'm just going to get a better pen actually, is the work done. Now the work done in producing this extension is the area under the graph. So what you need to do is you can't just measure simply the height. You need to measure sort of the irrespective, sort of the Y gain sort of thing if you've done that before. You need to work out how much each one of these boxes, you've got like a little box here, each one of them is worth. The work done is force times the energy. So you need to work out how much one of these are worth, how many squares there are, times it by how much each square is worth, and that gets you the overall work done. So I'm just going to write out the answer, and hopefully that little introduction there has sort of done it already. So when you measure it, you should get that there are about 12 or 14 big squares, or 318 small, plus the area, plus 8. So I'm just going to put 13 squares. So I've calculated that there are 13 big squares, 13 big. So that's, hopefully that makes sense. And the area of one big square is 10 times 0.05 meters. So 10 times 0.05 equals work done of one square. And then 10 times 0.05 equals work done on one square, and that equals, it should equal 2, times 10. It's 0.5 newtons. Is that right? And you times that by 12 or 13, whatever you've got. So I said it was 13 squares. And as long as you state how many squares there are and what area, you'll get a mark for it if it's between 12 and 13 big, or 318 plus or minus 8 squares, mini squares, for the small one. And if we do that, we should get 13 over 2, which is equal to 6.5 newtons. So the total work done in extending it is 6.5. So the way we've done that is we've worked out the area, we've drawn a line up from 3, we've drawn a line across, the area up to 3, up to the curve, to the loading curve, which is A. We count the amount of squares, which would have taken a bit longer than what we just did if you did it in the exam. So you might need to factor that in. Right, hopefully you can still see that and it's not going all fuzzy. So I'll zoom in again if it hasn't quite worked. So you can see we've worked out the area of the red bit, 13 squares times by 0.05, worked on 1 square and we times by 13, so we've got 13 squares, and that's got us 6.5 newtons. And you can see there's no permanent extension of 5A. And that's so that's the obviously it's not perfect diagram that I've drawn on there, but you know, it'll do. Hopefully. That's gonna bugger me if you can't see that. Hopefully you can. Might be this pen. Mind. Try and draw it a bit bigger next time. So, what's the next question? Wait 1 sec. That should be 0.3 meters actually, sorry. It says, assuming that line A is linear to an extension of 0.4 meters, 0.04, sorry. Calculate the Young's modulus of the rubber for small strains. So what we do is, first of all, we draw our line up from 0.04 meters, and we draw that across, and we see what that gets us. So each little square is representative of 0.01. We draw it up, and we should get 10 newtons. So this should be 10 newtons. I'm doing this now on my computer. 10 newtons at 0.04 meters. So that's our load. It's 10 newtons. So we know the extension. We know the unstretched length, which it tells us. So you know what you need to do? T equals 10 newtons, delta L equals 0.04. Now this is before even writing the equation, is 0.04. The length, which you just put as L, and that's equal to 0.5 meters. The cross-sectional area, which we don't need to work it out, but because it's told us, is 5 times 10 to the minus 6 meters squared. Otherwise we would have had to work this out. Always give it that. It says work out the Young's modulus. Now luckily we don't have to rearrange the formula, we can just use the formula it gives us, which is A equals TL over A times delta L. And that's your formula. We simply substitute our values in. So E is equal to TL, which is T, 10 times 10 newtons times 0.5 meters over 0.04, which is delta L, times the area, which is times, I'll put this in brackets, 5 times 10 to the minus 6 meters squared, and it gives us a Young's modulus. As you can see, this is going to be a very big one, of 2.6. 2.5 times 10 to the 7 pascals. 2.5 times 10 to the 7. You could have 2.5 times 10 to the 7 Newtons per metre even. But pascals is a more accurate way of measuring that. So you can see E equals 3 times delta L. We've substituted our values. Oh yeah, and then we've simplified it down to get our answer there. Right. So hopefully you've understood that what I've done so far. Now for these next two questions, I'm not going to write anything down because there's not that much left. But I'm just going to explain it, and hopefully you understand where I'm coming from in terms of the answers. So for the next one, it says on figure 5, draw the load extension line of the spring up to a load of 15 newtons and label it. So here's gone. So you basically draw a straight line through the origin, finishing at the same point as the rubber division, it says. So it's just a straight line. So we'll draw another graph up here. Straight line, 50 newtons. It's quite a simple line, that. If you can see it quite well. It's just up there. You just draw it up to 50 newtons on the left, and that will give you your answer. Obviously you draw that on that graph over there, but I've just put on the side things so it doesn't muddle it up for you. And then it says 5D part 2, with reference to the spring, explain what it's meant by limit of proportionality. Now limit of proportionality is up to the point where it stops following Hooke's law, so it stops becoming linear. As there's only one mark, that's all you need to say. So that's the end of question 5. Hopefully you've enjoyed it, and we'll see you in the next video.